Hi, in today's video I would like to introduce you a very nice proof regarding the Fourier series coefficient. So as the following function shows, s of x equal to e sub 0 over 2 plus the sum as n goes from 1 to infinity, e sub n is multiplied by cosine nx plus b sub n is multiplied by sine nx. Okay, our goal, we are going to prove these both identities. The first one is b sub n as a Fourier coefficient equal to over pi is multiplied by integral as x goes from 0 to pi as x is multiplied by sine nx dx. The second identity, we have the square wave function of this we have the square wave function equal to 4 divided by pi is multiplied by the partial sum of the sine x as sine x over 1 plus sine 3x over 3 plus sine 5x over 5 and all the way down to the infinity. Okay, so now before I proceed with the proof, I'm going to show first identity. I'm going to use it as a tool. Let's talk a little bit about the Fourier function. In fact, the Fourier function is a component of both coefficient, the odd and even coefficient, as the function shows, e sub n and b sub n. Okay, sometimes you find the Fourier series function is involving just e sub n only as a coefficient. Sometimes the inverse, you find the Fourier series function in terms of b sub n. Okay, depends on usage. If we need odd function, we are going to choose odd function in order to get the e sub n eliminated from the system. So now let's proceed with the proof. I'm going to prove the first identity. So as we know, I'm going to apply the trigonometry formula. We have the cosine of nx by applying the trigonometry formula. We have cosine of n plus k equal to cosine of n is multiplied by cosine of k minus sine of n is multiplied by sine k. Okay, for the cosine n minus k, we have equal to cosine n is multiplied by cosine k plus sine n is multiplied by sine k. The first one is negative because this one is a positive. The second one is positive because this one is negative. Okay, I'm going to subtract equation number 1 from equation number 2. I will have 2 minus 1 equivalent. I will have cosine n is multiplied by cosine k will be cancelled out because one is positive, the other one is negative, and the last term will be added on the other one. So I will have 2 times sine n is multiplied by sine k equal to this one, to cosine n minus k minus cosine of n plus k. So now I'm going to integrate both sides. By integrating this one, I will have 2 integral as x goes from 0 to pi sine of nx is multiplied by sine nk dx equal to this integral as x goes from 0 to pi cosine n minus k dx minus as x goes from 0 to pi cosine n plus k x. Here is x dx. Okay, so now generally if I'm going to integrate this one, so now I will have 2 cases. We said this one equal to 0 if n different than k. So I will take 2 cases. If n is different than k, that's mean, let's take n minus k equal to m as a substitution. So it will be the same thing here because both integrals is turned into sine function. For the first function, I will have sine m over m, the bound from 0 to pi. So whatever happened in first integral, it will be the same with the second integral, okay? Because both integrals are going to be sine, both functions will be turned into sine. So this one, if you plug x with pi, the sine of pi equal to 0 minus 0, as you replacing x with 0. So this integral will be 0. This will be 0 as well. Okay, so the whole thing will be 0. So this implies sine of 0 to pi, sine as x goes from 0 to pi, sine nx is multiplied by sine nk dx equal to 0. Okay, this is first case. Let's consider the second case. If n equal to k, okay, this one will be different, because as you take in n equal to k, that's mean n minus k equal to 0. Okay, if you replace n with k here, n minus k will be 0, so that's mean cosine of 0, which is 1. Okay, so my integral, I will have from 0 to pi cosine 0 dx minus the second integral as n equal to k, that's mean cosine of 2k x as x goes from 0 to pi. So now the cosine 0 equal to 1, that's mean I will have integral of dx as x goes from 0 to pi minus 0, because we already proved this integral of cosine 2kx equal to 0 as earlier proof, because cosine 2kx is turned into sine function. That means sine function, the bound from 0 to pi, it will be 0. So that's mean I will have only this integral, which is pi. Okay, consequently my integral as 2 times integral from 0 to pi sine nx is multiplied by sine kx dx. Don't forget n equal to k in this case. Okay, so this one we found equal to pi. By dividing both sides by 2, I will have integral as x goes from 0 to pi sine nx is multiplied by sine kx dx equal to pi over 2. Okay, here is our proof. Now we have proven this one. Let s of x to be as a odd function okay, this means s of minus x equal to minus sx, because this is the odd function rule. So the second rule, we have s of x plus 2 pi equal to s of x, because the function is a periodic function. Okay, I have these two conditions. I will work on these both conditions, such as s of x as an odd function equal to b sub 1 is multiplied by sine x plus b sub 2 is multiplied by sine 2x, and so on and so forth, and all the way down to infinity, equal to the sum of b sub n is multiplied by sine nx as n goes from 1 to plus infinity. Okay, I'm going to bring this one down and multiply both sides by sine kx and integrate both sides, okay, in the same time. So now by rewriting this one, I will have s of x, I will leave this empty space, I will have b sub 1 is multiplied by sine x, I will leave this gap here, a plus the b sub 2 is multiplied by sine of 2x, and all the way down to the b sub k is multiplied by sine b sub k is multiplied by sine kx, and all the way down. Okay, now what I'm going to do now, I'm going to multiply both sides by sine kx, as I said before, sine kx. This one I will have sine kx, sine kx, sine kx for each term, and finally I will have sine kx. Okay, then I will integrate this one from 0 to pi dx. I will integrate all terms. As I'm integrating on left hand side, I will integrating on the right hand side as well. So I will have dx here plus from 0 to pi I will have dx. Finally I will have this integral as x goes from 0 to pi, this integral dx. I will highlight this one with a red color. So now if you look at each term, all terms are turned into 0, because earlier proof we proved this integral of sine nx is multiplied by sine kx, which is written on the same form. If we have n different than k, we will have 0. If we have n equal to k, equal to pi over 2. Okay, all terms they have k and n are different, except the last one, which is highlighted. Okay, because it's a last term. We know that the last term in the series we have always n equal to k, because there is a last term of the series. That's mean k equal to n. That's mean equal to pi over 2. All other terms will be 0. Okay, this one it turns to 0, this one 0, and all the way down, but this one it turns to pi over 2. Okay, now since I have pi over 2, I'm going to take bk outside of this integral because it's considered as a constant. So I will have my integral of s of x as an odd function is multiplied by sine kx dx, as x goes from 0 to pi, equal to pi over 2. The value of this integral is multiplied by bk. It's equivalent. I'm going to replace a k with n by multiplying both sides by 2 over pi. So we'll have 2 over pi is multiplied by this integral as x goes from 0 to pi of integral of s of x is multiplied by sine nx dx equal to bk, a bn, as a Fourier series coefficient. Now this one is proven. Let's set the square wave of this function equal to 1. Okay, so this one I will have 3 values, 0, -1, and 1. Okay, I'm going to graph this one. I will have this graph from 0 to pi. This function will be like this, and going down and going down until you get a -1 here, and going up. This is pi, this is 2 pi. For this one you keep going down from 0 until you get -1, and going in negative direction until you hit -pi. From -pi going up and keep going. Okay, this is wave function, as wave odd function. Okay, equal to these values. The 0 value, they vanish when you have x equal to 0 and pi. For the second case, when it takes number 1, when you have x is between 0 and pi. Okay, for -1, when we have x between -pi to 0, and from pi to pi, and so on and so forth, because this is periodic function. It keeps doing the same thing all over these intervals. Okay, so now what I'm going to do now, I'm going to determine the function square wave of this function. So for the coefficient, we already proved b sub n equal 2 over pi. B sub n equal to 2 over pi is multiplied by this integral by taking s of x equal to 1, because we're taking this function as a square wave function, equal to 1. So that's mean our coefficient become 2 over pi is multiplied by this integral as x goes from 0 to pi sine nx dx. So I'm going to calculate this integral as b sub n equal to 2 over pi. So I will have minus cosine nx over n, the bound from 0 to pi. By taking the minus sign outside, I will have 2 over pi minus 1. By replacing x with pi, I will have minus 1 to the n. By replacing 0 with x, by replacing x with 0, I will have minus 1. By multiplying both terms, with minus sign, I will get 2 over pi is multiplied by 1 minus 1 to the n. If you take a look at this term, now I will have two cases. If n is the even numbered coefficient b sub 2n as an even function, as an even coefficient, equal to 0, as we have proven here. For the if n is an odd, that's mean this one it turns to minus 1. So that's mean 1 minus 1 equal 2. This one to turns, if it's odd, this one turns to 2 over pi is multiplied by 2, which is 4 over pi. Don't forget we have n, okay, because this one is divided by n, 4 over pi n. That's mean this is the value of b sub n. Okay, that's mean b sub n is decreasing by 1 over n, is decreasing because the n is going up, this term is coming down. Okay, so now coefficient, you take this number b sub n equal to 4 over pi. I have depends on n. If you choose an n, if you have the first one is an odd number, I will have 1 over 1. If you choose the odd number here, this one is turned to 1, this term. So this one 0, because we have even numbers. All the even numbers are 0 over the coefficient 0. The third one we will have 1 over 3. The fourth one 0 over 4th, and all the way down. From this one I will conclude the square wave function. As we have before, we have s of x as an odd function equal to b sub 1 is multiplied by sine x plus b sub 2 is multiplied by sine 2x, and all the way down. Okay, by choosing this coefficient, I have proven this coefficient, I have calculated this coefficient s of x as a square wave function, because we have taken s of x equal to 1. So now I will have the coefficient, I will have 4 over pi is multiplied by sine x over 1 plus the sine of 3x over 3 plus the sine of 5x over 5, and all the way down. Okay, because if you take a look at here, all even coefficients were cancelled because they are 0. Okay, and all odd coefficient, we left with this one. because this is coefficient b sub 1 as we found before. Now we are going to replace sine x with this one. Now we found the square wave function in terms of this b sub n. Okay, so now I have done with this proof. As you know, there is another part left from this proof. We don't prove yet a sub n as a coefficient. In next video I will do a sub n as a Fourier coefficient, because I want to mix them together today, because I want to make the video too long. So now I have done with this problem. Just consider the subscribe. If you have any question or comment, just put it in the comment section below. Thank you for watching. I will see you in next video. Bye.